Okay, so we are going to talk about discrete probability distributions. So before we do that, we've got to know what a discrete random variable is. Anytime we refer to a random variable, is simply a data variable, and we are talking about data. But distribution is something that we create for a random variable. So we've mentioned these words before: distribution, discrete. Can you think of an example for discrete data? Like for chapter 1, section 1.2.
It's discrete, the one that you count. So
Okay. Sydney says discrete is the one where you count, it's a count type data. Continuous is where you cannot count. So can we think of an easy example for discrete data? Great. What else? Everything. What? Lemons?
No letters.
Lemons. Oh, man. How about outcome of a six-sided die? Do you believe that it is going to be continuous? No, definitely discrete. What are the possible outcomes that you can think? 6. Okay. What are they?
1, 2, 3, 4, 5, 6.
Probability of x is equal to 6. It's 1/6, and it is the same for every single outcome. So the probability is 1/6, right? This table where we have a bunch of outcomes here, probabilities there, should remind you of something from chapter 2. This table should remind you of something from chapter 2.
Frequency distribution.
One more word, you're almost there.
Relative frequency.
Relative frequency distribution. So this table is nothing but a relative frequency distribution of discrete data. We are just going to get more fancy with the terminology. Relative frequency is nothing but probability. Data is simply, we're simply referring to a random variable. So what we have seen in chapter 2 has a very technical terminology. So relative frequency is nothing but probability. So what we have here, which is a relative frequency distribution of discrete outcomes, for informal terms, this is simply the probability distribution of a discrete random variable. That A needs to come in for it to make sense. So we see what has happened. So a probability distribution, relative frequency distribution are one of the same, but this is for form. Okay. if we sum all the relative frequencies in a relative frequency distribution, what should we get? 1. So if I sum all these probabilities, what should I get? 1. Does it add up to 1?
Yeah.
Yes. So sum of all probabilities must be 1. 2, every single probability must satisfy the properties of probability. Do we agree? So I cannot have a -1 or -2 in there. I can't have a number bigger than 1. So no value for probability can exceed 1. It can't be negative. It can be 0, in which case it is impossible. It can be 1 in case it is certain. But if that happens, there is only one outcome for this random variable. Are we clear with that? Yes. Can you think of an example for a discrete random variable? Okay, so how do we find the probability? So what we have, the scenario is go to a restaurant, you order chicken wings. If you don't like wings at all, then don't order. Or it's 5, 10, 15, or 20. So what is the probability that the person will not order chicken wings? How do we find it? 9 divided by 31, and what do we get?
0.2903.
0.2903. Okay. 6.
8.1935.
12.
0.3871.
3.
0.0968.
1032.
Oh yeah, 23.
23.
323.
323. If we add all the probabilities, it is going to sum to 1. M is frequency divided by total relative frequency. We're just calling it as a probability. Going to put on a graph. You should be able to recognize something here, but visualizing it helps. So the percent of people who would order no chicken wings at all, about 0.29, so right there. 5 wings exactly, 0.19. 10 wings, we have 0.38. 15, 0.09, and 20.03. Good. That's just one restaurant. Well, some restaurants may not go in increments of 5. They might do it in increments of 4, right? Or increments of 6. It depends. So if this is the profile, what is the most likely amount of wings that person would order? 10. On average, how many do we expect? So if someone said, okay, we go to a restaurant and they don't have an increments of 5, but they do 6, 12, 18, 24. So based on this profile, which is more likely? 6, why is that?
Once you get higher than 10, it gets a lot lower, and the lowest is between 5 and 10.
Very good. So the majority lies over here, right? As you go farther, the probability decreases. So the chances are it's going to be somewhere here. So the average would fall somewhere here, and you can't buy 6.5 wings. You could eat 6.5, but you can't buy. So you round it to the nearest integer, because that makes sense, because we want it to be discrete. Another reason as to why I didn't connect these dots and draw it as a continuous line is because the data is discrete. Yes? We have seen a picture like this before. Go back and look at your notes, chapter 2, relative frequency distribution. We drew something like this before. So now we would like to know the average of this data. So that is our question. That average is what we call an expected value. Just a fancy term for average. So if a distribution is provided to you, we can find its expected value. So I want you to pick up your calculator, put all of the outcomes for y in list 1, the probabilities in list 2. So what I did is I put all the outcomes in list 1, probabilities in list 2, and we are going to find the expected value, which is simply the mean. So if you have the newer version of the calculator, you should see list, freak, and calculate. So in the list part, you put L1, the second one. In the freak part, L2, second 2, and hit calculate. If you have the older version, 1 mark start, second 1, comma, second 2. I believe I skipped that 1 mark starts part. So the list, freak, and calculate is under 1 mark starts. Good. And enter. X bar happens to be 6.97. Sophie gave me a number that's going to be somewhere between 5 and 10. I agree, probably around 6. And the average happens to be 6.9735. Which is approximately 7 rings. So if you go from a restaurant that goes 0, 5, 10, 15, 20, and you pick a random person who typically orders 5 wings, if that person goes to this restaurant, what are they likely to order? Or if they typically order 10 rings, what are they likely to order? If you can't get 10, all you can do is 4, 8, 16. You're likely to get 8 because the expected value is 7. So the closest that you can get is 8. Are we clear?
Wait, so we said 2 on.
Okay. So we have the expected value. Typically, what would SX be? Standard deviation. But in this case, it is missing, right? Does that mean that we don't have a standard deviation? No. The very next one has the standard deviation. which is the population standard deviation. We don't have a sample, rather we have a distribution. Anytime you have a distribution, the resulting standard deviation that you find is a population standard deviation. Does that make sense? So if you have a bunch of observations and you have a sample, then sure, you will get a sample standard deviation. But if you have a probability distribution, you'll only get the population standard deviation. Good. So sigma x here . 5.48. That's a lot of variation. And if the standard deviation is 5.48, what is the variance? What should we do to the standard deviation to get the variance? Square it. So variance is simply 5.48 squared. Good. And what do we get?
30.03.
That's it. 0. There is a lot of variability here. Can someone guess as to why? The deviation is about 5, right? One would think that's a large number. Because it's a small base. Okay, this is not a data set. This is a probability distribution.
It's a small probability distribution.
Wow, good try. No. The answer is in that picture. That's my hint. Well, of course, it's there too.
What was the question?
We have a large standard deviation. 5 is huge, right? So why did we get such a large number, and does it make sense?
Because it's 5 5s.
Very good. So we're jumping from 0 to 5, 5 to 10, 10 to 15. So the deviations are likely to be large, right? And not only that, the range is from 0 to 20. If we picked a lot of numbers, you know, if I can just order 1 wing, 2 wings, 3, 4, 5, and so on, this is probably going to reduce to a smaller number. We get a larger number because we're jumping in terms of size. Clear?
No.
Okay, so what we have is overtime hours, and that is what we measure, so 0 through 6. And these are the frequencies, but we have to convert it to a probability distribution. So you take each of those counts and divide by the total, which happens to be 192. When you do that, you get the probability values. So define the mean and standard deviation. If you have the new older version of the calculator, start over to count. Number 1, second 1, comma, second. Oops. Second 1, comma, second 2. So the mean is 3.4. Standard deviation, you can only get the population standard deviation because we have a distribution here. If you look at the data and look at the expected values, does it make sense? Even before you start the problem, you can do a process of elimination or an exam to kind of get to the correct answer, right? So if you have to take a guess without the answer, what would you have guessed? 3. Why 3? Or somewhere close to 3, but 1. Look at our previous example.
Majority of the employees are work 3 hours. Cassidy?
Cassidy says majority of the employees are right over here. So the average or expected value of overtime hours must be around 3, which is correct. We have 3.44. And Last time we had a large standard deviation. This time, not so much, because we are going in steps of one. Yes? How do we find the variance? Use square root. Okay. Any questions in this? No?